So in this problem, we have an interesting question, which is to show that the order, in our notation, we were using absolute value bars, so maybe I should stick to that. But in Pinter's notation, they write order, is the same for any conjugate. In other words, order is preserved by conjugation. This is in any group. Now, this can be proven directly from the definitions, and I think that might be worthwhile to try. Critically, this absolute value notation is not multiplicative. So don't fall for any trap like this. This doesn't make any kind of sense. Because the absolute value bars are talking about the order of elements. And if that was true, these would have to be order 1 to get back to here. And that's not what we're trying to do. So we're saying these things are equal. And while you can absolutely do this from first principles, I want to show you a proof that uses what we saw previously about Cayley's theorem, because that makes it super duper easy. So take G and regard it as a permutation group by Cayley's theorem. Therefore, there is some isomorphism that sends A to some permutation which we called pi A when we were talking about Cayley's theorem. Now, the magic here is that this has some kind of cycle description. As a product of disjoint cycles. Now, what happens to BAB inverse? BAB inverse under this isomorphism goes to pi B, pi A, pi B inverse, which is the same thing as pi B, pi A, pi of B inverse, because it's an isomorphism. So inverse of B is sent to the inverse permutation. This is a conjugation. And we know what conjugation does to cycles. Conjugation preserves cycle types. We're writing a lot of exclamation points today. We're very excited. This is a cool proof. So the upshot is the order of an element in Sx was determined by the not the multiplicity, but the divisibility properties of the constituent cycles. Since cycle type is preserved, these are the same. Very cool. Now, I'm realizing after doing this that there is still one issue. But since I like this proof, I think I'm going to leave this here, which is that the statement that the order of A being the same as a conjugation, well, I'm cheating a little bit here when I'm using this Cayley's theorem and this cycle stuff, because I'm secretly using that this group is finite. This requires the group to be finite, as there are permutations in some Sx, that's not an X, which have infinite cycle decompositions. Or does it require it? Is it okay that the cycle types be infinite? Is this a problem? I let you think about that. Um, I trust that I at this point we have enough group theory knowledge to figure out if this is an issue here.